This PowerPoint is over the Unit 12 review questions. So the first question, in the forging process, a blacksmith will hold one end of a metal bar on a hot fire and hammer it out and to shape it. Explain why they still have to wear a heat-resistant glove to hold the other end, even though that end is not put directly in the fire. All right, so this gets to conduction, where heat conducts. Heat conducts through the metal and transfers to the other end of the bar. And because heat transfers through the bar to the other end, that'll make that end hot as well. So that's why he has to wear that glove in order to protect his hand as that heat transfers. Question 2, often the architects in the U.S. design most of the windows of the house to be on the north side. How does putting windows on the south side affect the heating and cooling of the house? So in the northern hemisphere, the sun rises in the east and sets in the west, but the sunlight always comes from the south. And that might be a little confusing, but I'll show you a diagram here in a second that shows this. It says the sun's light would help heat the house in the winter, but also in the summer, which is when you don't want the heat. So the windows use the process of radiation to bring the heat into the house. So let's talk about why the sun always comes from the south, even though the sun rises in the east and sets in the west. So if you can imagine the earth and the sun, the sun's rays shine directly onto the earth, but the earth is curved, which means it hits directly over this part right here, the Tropic of Cancer and Tropic of Capricorn, and on the equator. However, as you get north or you get south from the equator, the earth curves, so it's not a direct sunlight, it's actually at an angle. So if you were to think about the sun as it goes from east to west around the earth, and if you were to build a house in the northern hemisphere in the United States, then what you see here is that as the earth is spinning, that the light will hit the south side of the building every time. Now that's because of the curvature of the earth. Now if this building were at the equator, it would hit the top, so there wouldn't be much of an issue, and you would just get the east side and the west side as the earth rotates. But since it's curved, the building is actually tilted up a little bit compared to the sun, and it always hits the south side. So putting windows on the south side uses the process of radiation to transfer heat into the building, which is good for the winter, but not so much for the summer. Question number 3, you can hold your fingers beside a candle flame without harm, but not above the flame. See the figure to the right. So why is that? Well, convection moves hot material upward. So the convection of the heat will actually rise pretty quickly, but conduction to the side does not move very quickly. So there is heat that comes off the side, but it's not as fast as the convection is going to be going upward. So again, the heat going up is by convection, the heat going to the side is by conduction. Question number 4, how does a star form? A star forms when contracting nebula becomes dense and hot, and that's an important part. Dense and hot, the temperature increasing means that the particles within that nebula are going to be moving pretty fast, and that kinetic energy and getting those particles close to each other is what starts this process, and that's nuclear fusion. So once nuclear fusion begins, then that's when the star is formed. Question number 5, when a star comes to the end of a red giant stage, which is much like the mass of our sun, explain what happens to the center and outer layers of the star and why. So first off, the center will become a hot, dense white dwarf. And now the reason of that is because nuclear fusion pushes out what we call nuclear pressure. But then when the star dies, essentially that nuclear pressure is gone. So gravity pulls the core in really fast. And that means all that heat is stuck there. And it's essentially white hot, which is why it's a white dwarf. But the outer layers are not being pulled on very hard anymore, so the outer layers actually come outward, and it's called a planetary nebula on the outside. So the inside is a white dwarf, and the outside becomes a planetary nebula. So the major similarity and differences between a star that becomes a neutron star and one that becomes a black hole. So first off, the similarity is that both of them will end their lives with a supernova explosion. However, the major difference is the size, the mass of each one. So a neutron star is less mass, and it says here a black hole is more massive than a neutron star, and it's actually so massive that light cannot even escape. Question number 7, explain where meaning the plate boundary, and how mountain ranges are created on the Earth. So mountain ranges are actually created from a convergent boundary. So the plates will come together, and as the plates push together, one plate gets pushed upward, and that's what creates the mountains, and then the other plate gets pushed down. The less dense plate gets pushed up, the more dense plate gets pushed down, and then the one that gets pushed upward creates the mountains. The one that goes down gets recycled back into the Earth, and that's a process called subduction, where a plate gets pushed down and recycled back into the Earth. Question number 8, explain where, meaning plate boundary, and how, naming the process, new parts of the crust are created on Earth. Okay, so this actually occurs at a divergent boundary. So the seafloor spreading, so this is the process. As the seafloor spreads and they diverge away from each other, that leaves a gap in between. And within that gap, the magma comes up in between, and it essentially, because there's no resistance to that magma, it comes up and it actually builds a little bit of a ridge. So down the middle of the Atlantic Ocean is a ridge caused by divergent boundaries. As the plates separate from each other, the new material, the magma comes up between, it hardens, and it becomes new crust for the Earth. So number 9 says a geologist finds a plant remains that contain 5 milligrams of a radioactive isotope carbon-14. If it was determined that the plant started with 80 milligrams of carbon-14 when it died, how many half-lives did carbon-14 go through? All right, so in order to figure out how many half-lives, we basically start with 80 milligrams, and then we're going to divide by 2, and that gives us 40 milligrams. So that's the first half-life. Then we divide by 2 again, we get down to 20. That's 2 half-lives. Then we divide by 2 again, we get to 3 half-lives. That gives me 10 milligrams. Then we divide by 2 again, we get down to our 5 milligrams of remains, and that's 4 half-lives. So since that 5 milligrams is what we end up with, and that means we have 4 half-lives for the carbon-14. Now, given that if the half-life is approximately 5,700 years, how much time has passed since the plant died? So if we have a total of 4 half-lives and we have 5,700 years, then we take the amount of time it takes for a half-life, so that's that 5,700, times the number of half-lives, which is 4, and that gives us the total time passed, which is going to be 22,800 years. Number 10 says an earthquake shakes a location and sends out seismic waves. The graph below shows the time that the waves travel and the distance for those waves from the epicenter. So part A1 says, based on the graph, if the earthquake occurs at 4,000 kilometers from the seismograph station A, how much later does the first P wave arrive at the station? So we go to 4,000 kilometers, and then we go up to the graph where the P wave hits, and we see that that's going to be at 6 minutes. Same question, except now we're looking at the S wave. When does the S wave hit that location? So again at 4,000, but then we go up to the curve for the S wave, and that is at 13 minutes. The third part of A says that based on the graph of the earthquakes occur at 4,000 kilometers from seismograph station A, what's the difference between the first P wave and the first S wave? And this is referred to as lag time. So remember, the S wave was 13 minutes, the P wave was 6 minutes, so the lag time is going to be 7 minutes. And that essentially is the distance between these two, the amount of time from the P wave to the S wave. So subtracting those, and that gives us our lag time of 7 minutes. Part B says the first P wave of the earthquake arrived at the seismograph station B a little more than 12 minutes later. The first S wave arrives at station B. So that means the lag time between the S wave and the P wave is going to be 12 minutes. So it's asking how far away is the station B from the epicenter. So what we're looking at is we're looking at a lag time of 12 minutes. So if I make this basically this arrow right here that goes from 0 up to 12, I'm looking for a space between these two waves that is going to be 12 minutes. So I move this until I get that between the two curves, and you can see that 12 minutes is about right here, and we go down to the distance, and that distance is, well, this is 6,000, this is 8,000, so halfway in between is 7,000, and then 7,000 to 8,000, halfway between that's going to be 7,500. So about 7,500 kilometers, that's how far away station B is going to be from the epicenter.